Hey everybody, my name's Chris and I'm going to be talking to you today about 4 infrastructure trends that I'm excited about, and I'm going to try and cover that in 20 minutes. It's a somewhat ambitious goal, so let's get started. First off, a little bit about myself. I'm an engineer, investor, and author with about 20 years of experience in Silicon Valley companies like PayPal, LinkedIn, and WePay. And the majority of my time I've spent doing infrastructure development in those companies. I've also worked a bit on open source. I wrote a stream processing system called Apache Samza while I was at LinkedIn. And more recently, I've worked on Apache Airflow. These days, I fill a good chunk of my time doing writing for a newsletter called Materialized View, where I try and cover interesting topics and conversations around infrastructure development. I've also written a book called The Missing README along with Dmitry Ryaboy, my co-author. And the book's, essentially a software development guide for new software engineers that are just kicking off. And it tries to get engineers up and running at companies in their first couple of years. Okay, so for this talk, I'm going to try and cover four different topics rather. The first one is going to be object storage. The second is going to be about how we're decomposing databases. And then we'll wrap things up with a brief overview of what's going on in the land of Postgres and durable execution. The goal here is really to give you a sample of what's going on and leave you to dig in deeper on topics that you find interesting. So for starters, I've got object storage. If you think about the way that systems used to be built, they were usually responsible for managing their own persistence. And what I mean by that is writing data to hard disk. And inevitably, when those systems try to scale, they end up needing to have the data on more than one machine. That leads to a couple of problems. The first of which is it's actually pretty complicated to manage the storage for things like durability. You end up having to replicate data. You end up having to manage consistency of the data. And that introduces a lot of complexity, and it's just hard, right? And the second thing is, as we've shifted to the cloud, persisting all this data on local disks or NVMe or even elastic block storage can be quite costly. So the statistics here that I've got on the slide are actually from a talk about S3. Amazon had this kind of cute talk they gave recently where they talk about building a somewhat large storage system. And as you can see, S3 is pretty complementary to the challenges I've mentioned. It's pretty cheap, so the cost for persisting data in object storage is actually relatively low. And it kind of handles a lot of the replication challenges that we've seen historically for you. So you get huge durability, it manages replication within a single region across availability zones, it can scale up. And so a lot of systems these days are starting to think about adopting S3 as a storage layer for the data that they need to manage rather than going straight to disk. And there are kind of 3 ways that this happens. The first, and I would say most incremental way, is tiered storage. So in this mode, data is just replicated the way it normally would be. The system more or less looks as it did before. But for data that's accessed less frequently, the data is put into object storage. And the goal mainly here is to reduce cost. The next level up in this hierarchy is what I'm calling a write-ahead log-based architecture, where you have a write-ahead log, which is essentially an append-only log where you're appending mutations for your data, so inserts, updates, and deletes. And that's going to live outside of object storage, but most of the other data is going to live in object storage itself. So it's almost the inversion of the tiered approach, where you're keeping only the newest data out of object storage rather than only the oldest data in object storage. And a canonical example that I like to use here is a system like Neon, which is a Postgres system that uses object storage for essentially bottomless Postgres data. And again, the goal there is really about reducing cost, but having the wall means that you continue to have transactional guarantees and also a lower latency than you might otherwise see with object storage. And last but not least is zero disk architecture, which is a term coined by a company that I've invested in called WarpStream, where they essentially abandon local disks altogether. And all the data goes straight into object storage. And the advantage here is it dramatically simplifies your architecture and the code you need to write in order to build the system, because your nodes essentially become stateless at this point. And you use S3 for all the replication, all the durability that you need. So you can kind of spin up nodes as you need to scale and spin them down as you're done. It also again, can make things quite cheap. You do need to consider the API cost for interacting with object storage a little bit, but if you manage that properly, you end up saving a lot. The trade-off here is the latency can be a bit higher, right? If all the data needs to be persisted to object storage, every write is going to be considered durable only when it makes it to object storage. Then you've got to wait for that write to occur. Similarly, you have to wait for reads to occur. And object storage is just never going to be as fast as local disk. But for a lot of use cases, that's fine. So the implications here are, first and foremost, it should simplify things, both operationally and in the code we write. System should be easier to build because you don't need to worry about things like quorum writes or raft. It should be easier to operate because systems become more stateless. It should be easier to integrate. This is something that I'm still thinking about, but the idea here is if all your data is in object storage, the data integration story that we've been telling for about the past 10 to 15 years that typically involves something like Kafka or even something like Workflow Orchestrator changes, right? You no longer need to have Kafka between your OLTP database and downstream systems. Instead, everything's already sitting on object storage. So perhaps your Prefect jobs are just reading from data from one system and writing it to another, both of which are just different buckets or directories within object storage. And then secondly, it gives users more control to decide how they want to balance between cost, latency, and durability. So some users might decide that latency is really critical, but they care less about durability. So they might relax the constraint and be comfortable with some data loss. For other users, they might decide that they want data to be very durable, and they also want low latency, in which case they're going to be paying a lot more to interact with object storage. Next topic of the day is, I've entitled it Databases Are Splitting Up. It goes by other names. I think some people will call this composable data systems or database decomposition. But the idea here is that traditionally databases have been fairly monolithic. Every database includes its own storage layer, its own query engine, its own set of optimizers and execution runtimes and so on. And what we're seeing lately is that some projects are starting to break this apart and expose these layers separately. So for a quick overview, when you think about a query engine and you write a query for a database, you're typically writing a SQL query in text. So inside, the database is going to take that text, it's going to parse it into an intermediate in-memory representation. Once it's in an in-memory representation, it's going to optimize that representation to try and make your query faster for you. And then it's going to translate that optimized in-memory representation into a series of operations on disk. So it could be a read, it could be writes, it could be doing joins, and so on. And again, every one of the databases historically has had all these components, or most of them. So MySQL has its own stack for this, Postgres has its own stack, Trino, Presto, they all have their own stack, right? And if you look at it, a lot of these operations start to look fairly similar. So projects like Data Fusion from Apache or Meta's Velox, there's a system called Substrate as well. What they're doing is building libraries that are taking these chunks out of the database so that they can be shared and leveraged across different databases. So what does this mean? Why are we doing this? There's obviously some added complexity when you break things apart. You have to be much more clear about the APIs that you're defining. But the advantage is it makes new databases easier to build. If I can take something off the shelf, then I can spin up a new database pretty quickly. And that database is going to be actually pretty reliable because it's using libraries that have been battle hardened through usage for many years. The other benefit you get is you get to, share and accelerate the features and performance of the libraries that you have. So, for example, if I have an optimizer and I decide to make an improvement to that optimizer, well, everybody that's using that optimizer library is now going to get that benefit, right? And similarly, if I add a new feature to my query parser, everybody who's using my query parser is now going to get that new feature. So it should dramatically accelerate the speed and features that we get across all the databases that we have as long as we're sharing these systems. And lastly, it allows developers to focus on what matters, especially infrastructure developers. So if I'm building a database and my big differentiation is that I'm going to build it for maybe observability data that's time series based, and I have some fancy new storage format that's going to do that really well, and it's going to optimize for those kind of queries. Well, rather than having to build my query parser and my optimizer and my intermediate representation from scratch, I can just take the off-the-shelf solutions from something like Data Fusion or Velox, and I can spend all my time building this really amazing storage layer, right? So it should really allow developers to build new systems easily and effectively. Now, there's a trade-off here. The question is, does this kind of commoditize databases? If everyone is using the same libraries, won't we all see the same performance and have the same feature set? What's the difference between these databases? And I think in some cases it will. There's a really good blog post from a developer named Jordan Tigani, who's the CEO of MotherDuck, where he talks about how performance is becoming increasingly commoditized. But I think it also opens up opportunities for us to focus on other areas of the database. So I kind of break it into three distinct sets. The first one is around building database platforms. So when you think about a database, there's a lot more to running a database than just starting it and querying it. You have to manage schemas, you have to manage backups, potentially branching data or time travel going back and forth in time. You have to manage data integration. So there's an opportunity to spend a lot of time building out really excellent platforms for developers that help them run and interact with the databases they need. The second space is databases for specific verticals. And so you're starting to see a bit of this here. My two favorite examples are a company called Nile and another company called Tiger Beetle, both of which are companies that I've invested in. And excuse me, Tiger Beetle has built a database that's built specifically for finance, right? So it's a double entry bookkeeping database, which is like this classic way that accounting happens. And Nile has built a database that's specific for SaaS. So they understand if you're a SaaS company that you have a bunch of tenants, a bunch of different customers, and they in turn have users for their individual organization. And so it has baked that directly into Postgres so that you can build systems for SaaS relatively easily. And the key idea here is that you get really hyper-specific vertical databases that address users' needs that kind of bleed their way into business logic. And then the final category of databases that I see making a resurgence because of this are multi-model databases. So traditionally you have something like Postgres or MySQL that does OLTP workloads, which are your traditional online production query loads. And then you have analytic databases, OLAP databases that handle select, count, group by more analytic queries. You have geospatial and search engines. And traditionally each one of these systems has been its own engine, its own system, because each one has a different query pattern and needs to persist and store data differently. I think as we're seeing these libraries come available, we're starting to see a lot of these use cases merge because it's a lot easier to combine them when you can focus on just the storage system in order to handle both OLTP and OLAP workloads. And so I'm excited to see how that evolves. All right, for my third section, I want to talk about Postgres. You kind of can't talk about databases without talking about Postgres. And Postgres has been having somewhat of a resurgence lately. In fact, after about the past 10 years, it's really grown quite a bit. So if you look at this chart from DB Engine's ranking, you can see the orange line there is Postgres. And the thing that may not be obvious is this is logarithmic axis. So it's actually growing non-linearly here. The other lines are MySQL, SQL Server from Microsoft, and Oracle. And the question is why is Postgres growing so much and the other ones are remaining relatively stagnant or even dropping a little bit? I think for starters, a lot of the critical parts of Postgres that people have been negative on have been fixed. So specifically performance. The performance for Postgres has been largely, I would say, addressed over the past few years when compared to something like MyISAM or InnoDB, which are MySQL storage engines, which traditionally have been viewed as maybe a little bit faster. It's also got a fairly liberal open source license when compared to something like MySQL. So Postgres is much more MIT or BSD-like, which means that companies tend to be a little bit more comfortable building out of it, on top of it, and extending it. It's also mature, right? It's just been around a long time. People are comfortable with it. It's got a good ecosystem and a good set of tools, so that should drive some adoption. But I think the thing that's really driving a lot of the adoption here is this flexibility. It's not immediately obvious, but PostgreSQL is very extensible. It has a kind of a plugin extension framework that lets you add new features to it. So you can extend everything from the SQL grammar to even the data types that it has, the storage engine and table formats and so on. And this has really created an interesting flywheel where As developers are adopting Postgres more, it means that the infrastructure engineers are more comfortable and encouraged to build on top of Postgres, since that's where all of the users are. And consequently, as they extend and add new features to Postgres, it means even more new users come and use it because it addresses more use cases, right? And so the way that we see this playing out is essentially bifurcated in two different ways. The first way is that infrastructure engineers will build a database that is entirely separate from Postgres, but they'll maintain compatibility with either its protocol or its dialect, right? So this could be the replication protocol, which means that their system can read data from a source Postgres replica or replicate it to a downstream replica, or it could be the SQL dialect itself. So you could actually write, SQL that looks like PostgreSQL, but in fact is running on another database. So a classic example that I like to cite here is something like CedarDB, but many NewSQL databases use this as well, Yogabyte and so on. The other approach is more of an extension one, and so in this world, rather than writing a new database from scratch using maybe the composability stuff I had mentioned before, you instead take Postgres and you extend it by writing an extension using its APIs, or perhaps you extend its storage layer. The storage layer example, again, I always use is Neon, where they've taken sort of a vanilla, pretty standard run-of-the-mill Postgres, but they've made the wall, the write-ahead log that Postgres has, they've made that remote, right? And so that now writes into an external storage layer, and then they replicate that data into object storage. So the implications of this are we should start to see a somewhat smaller operational footprint. If Postgres can service more of our needs, for example, maybe we've got an extension that allows us to use OLAP queries, which are these select count group bys on large data sets in Postgres. Well, maybe we no longer need a separate data warehouse. If we have an extension like ParadeDB's, vector search and search library, well, then maybe we don't need an external search engine like Elasticsearch. We can just use Postgres for that. So fewer operational systems means less pain for the operators. It also means shared tooling, right? So if I have a bunch of tools that can wrangle Postgres, well, that's great. I can use them for these new things as well. And the second implication here is that systems just need to speak Postgres now. In order to get data into your system, you probably want to replicate it from a Postgres feed. Otherwise, you're going to be having to do some sort of change data capture, Kafka-based data integration thing. And likewise, if you're building a BI tool or some client thing, you probably want to speak Postgres because there's so much adoption and growth there. All right, final topic. We are talking about durable execution now. And this one is, I would say, maybe a little bit complicated, so bear with me. I'm going to do my best to try and explain it. But durable execution is essentially this new programming paradigm that's kind of come to the forefront over the past 5 years or so, where developers are using a framework that tries to help them manage failures, right? And so the most concrete example I can give is if I'm doing payment processing, perhaps I want to debit a bank account and then credit another bank account, right? I want to take money from one bank account and give it to another. And if I fail halfway through that process, I might have debited the first bank account and not credited the second. And in a database, you would just have this wrapped in a transaction, right? But as we go to distributed systems, not everything is fully transactional across all these distributed systems, be it microservices or non-transactional data stores. And so you need something to help you manage this transaction. And durable execution does that. And the way that it does that is by shimming itself between your code and the data that you're reading and writing, or the API calls that you're reading and writing. And it essentially logs everything that you see and everything that you do, so that when a failure occurs, it restarts from scratch. And as the code runs through, it discards anything that was already successfully done and anything that was already successfully read, all the way up to the point where you failed. And then it allows the reads and writes to start going through as normal. Sounds great, and it has a ton of implications. I mentioned payments, e-commerce, logistics, gaming, SaaS. In fact, really anything where you have exactly once behavior that you want to have happen, it's useful for. And it turns out like essentially that's anywhere you would have a transaction in a database. But again, because we have all these distributed systems spread all over the place and networks are faulty, we can't just use a database transaction the way that we would before. The problem with this is it's hard, right? So the frameworks are trying their best. I've got a screenshot here from a company called Temporal, which is sort of the leader in the durable execution space. And I'm not trying to pick on them. I think they've done a fantastic job. And have done a great job not only of making it workable, but of sort of extolling the virtues of durable execution. But the reality is it's still just very difficult to write durably executable code. And so you can start, and this is an example from their documentation, a screenshot I've taken. You can start with a very simple question about what is a workflow definition, and then almost immediately it falls apart into this discussion about non-determinism, and you kind of end up having to get a PhD in deterministic code in order to be able to use durable execution frameworks, right? So there's a really good post from a fellow named Chris Gillum, who's an engineer, used to be at Azure. I believe he's working somewhere else now, where he wrote Common Pitfalls for Durable Execution Frameworks. And he outlines a number of challenges, but I think the two most important one are this concept of non-determinism, and related to that is the problem of code deployment. So for a refresher, non-determinism is the idea that if I give my code the same set of inputs, it might produce a different output the second time around. And that sounds kind of strange, but when you think about it, it's actually very common. So random number generators are non-deterministic. Depending on a clock is non-deterministic. And in fact, making calls over the network, any kind of I/O can actually be non-deterministic because things outside of the code can change the data on the disk, or a network can fail and you can have to rerun it and so on. So with the way that durable execution frameworks handle this is they essentially force you to use wrappers around all of these places where non-determinism would be introduced. And that's great if you can remember to use those wrappers, but it's not always easy to remember that you've got a non-deterministic chunk of code that you need to wrap. And the second issue that I think is challenging is the fact that even changing your own code can introduce non-determinism, because if you recall, the durable execution framework is logging every read and write that you're doing, every mutation, every API call that you're doing, so that when a failure occurs, it can discard the stuff that has already been successfully executed. But if you change your API call order or introduce a new API call, you get an issue where your code is no longer compatible with the log that the durable execution framework has. And this can be really difficult to deal with. So the net of this is that this can't be the end state. It's just too difficult for most application engineers to work on this stuff. Fortunately, there's a ton of research going into this space, which has me really excited. It's sort of, I would say, one of the more academic, researchy, open-ended spaces in infrastructure right now. So traditionally, developers have used SDKs to interact with these systems, where you're very aware that you're working with durable execution, and you're, again, wrapping things that are non-deterministic and interacting with the frameworks. And that's very flexible, but it also is complicated. But we're seeing three new ways in which durable execution is being explored. The first of which is really around language primitives. So for languages that have async await semantics, i.e. Python, JavaScript, Rust, there's a set of projects, the most notably one is Resonate, that allow you to put a runtime in between the language and your code that will actually do the async functions, not only asynchronously, but distributed, and then it will manage the durable execution of those async functions for you. So if an async execution fails, it will replay it and try and guarantee it happens exactly once. And your code continues to look pretty normal, just an async await API, the same as it did before. But under the hood, you're getting durable execution, which is great. Go coroutines are another area that's also being explored that's kind of similar to this. The next level up here is stream processing. And the idea here is, if you think about the challenges that you're facing with durable execution, things like exactly once semantics, managing state, schema evolution. These are actually problems that have existed in stream processing for decades, and that we've been wrestling with on the stream processing side of the house for a long, long time. And so there are a number of projects that bump up against this. I think Flink has stateful stream processing. Kafka Streams has stateful stream processing as well. Everyone's thinking about how to manage event schemas as they evolve over time. And so there are a lot of projects in this space that I think can serve some of the durable execution use cases. And that's an important thing I want to underscore here, is that some of the projects are exploring what can we sacrifice from the durable execution use cases in order to make the interaction model easier. And so, excuse me, I think in the case of both stream processing, workflow orchestration, and even async await for that matter, they're deliberately foregoing some of the stuff that you might be able to do in the SDK, but the advantage of it is it's easier to do, right? Moving on now to workflow orchestration, the last one on the list. This is something that should be near and dear to everybody's heart that's listening to this. But essentially, again, if you think about workflow orchestration's challenges when it comes to failure, they start to look a lot like durable execution. What do I do if a task fails? What if the task externalized some state? What if it created a table? What if it wrote some rows to a database? How should we handle that? Should we replay? Should we retry? Should we roll back? These are all things that durable execution has to think about as well. And this is actually something that I'm really excited to see Prefect thinking about with Prefect 3 and their state management and durable execution and exactly one semantics that they're providing with the new release. Because I think, again, while it's not a full durable execution framework, it does start to address and eat away at some of the problems that we've been talking about. Okay, we are now probably a little bit over time. I just want to take 1 minute to say thanks for sitting through the talk. I hope you enjoyed it, and definitely feel free to reach out to me. I'm on Twitter and Blue Sky, and don't forget to subscribe to my newsletter at materializedview.io.